Welcome back for part 2 of the circular motion lesson. Now, we had the particle here, particle A, travelling around a circle, and it was a fixed distance away from the origin, the radius, took a time of t to do one lap. The position in relation to the x-axis is measured by the angle theta. The angular velocity is theta over t, so that's any angle divided by the time it took to get there, or 2 pi over the period. And then the tangential speed turned out to be omega times r. That's a pretty important relationship, so I might just give that one a number there, equation 1. This one, equation 2, that's the position vector in relation to the origin, and this one, equation 3, that's the velocity vector of the particle. And we saw a nice little animation of that. Now, the purpose of this one, the main focus of this one, is we want to know about the acceleration of the particle. And it is the time derivative of velocity. So let's do this. Derivative of sine is cosine, omega t. So derivative of omega t is omega, so it'll be negative r omega squared using the chain rule. Derivative of cosine is the negative of sine. So I'll have sine omega t by j, and it was negative of this, so it's negative r omega squared. That's our acceleration vector. Now that doesn't look particularly nice to me. So I'm going to make a little comparison between this and what we had back in equation 2. Notice that there was r cosine omega t. We definitely have r cosine omega t. And we had r sine of omega t. We definitely have that as well. But we've had this negative omega squared as well. So let's take a factor of negative omega squared, and we'll be left then with r cosine omega t I plus r sine omega t j. And what we have there is the position vector r. So a, as a function of time, is negative omega squared multiplied by the position vector. This is a vector equation, so it tells me, omega, remember, was just a number, so the negative sign tells me that the position, the direction of acceleration is exactly opposite the direction of the radius vector. Let's explore that for a minute. If our particle was here, that's the radius vector r, pointing from the origin to the point where our particle is. But the acceleration vector is pointing in exactly the opposite direction, towards the centre of the circle. Now, it wouldn't really matter where the particle was. If the particle was over here, the radius vector for the particle has changed. Radius vector is a function of time, it changes as time advances. The acceleration vector is still in the opposite direction. So the acceleration vector is always going to point towards the centre. There's a name for that. It's called centripetal. Acceleration. And it literally means centre seeking, pointing to the centre of the circle. And this is a very important relationship. Very important indeed. Isn't that magnificent? Now, we can go back to our GeoGebra simulation, and I can turn on the acceleration vector here in green. There it is. And I can make the time advance. And notice acceleration is always pointing towards the centre of the circle. Notice that velocity is always tangent to the circle, and therefore the velocity and the acceleration are always perpendicular, because a radius and a tangent are perpendicular no matter what point on the circular path we're looking at. This is important. The acceleration is the vector that changes the velocity. There is no component of the acceleration which is in the same direction as the velocity. This is why the acceleration doesn't make the velocity increase or decrease in size. It merely makes it turn. A constant speed around a circle is not uniform motion. There is an acceleration present, and as you would know from physics, if there is an acceleration present, it means there is an unbalanced force causing that acceleration. Accelerations are caused by unbalanced forces. Now, what causes that force? It could be any number of things. This diagram could represent the solar system. Point O would be the sun, point A could be the planet Earth, and the force from the sun, the gravitational force from the sun pulling towards on the Earth, always pulling inwards to the centre, is what keeps the Earth going in its circular orbit around the sun. It could be a ball tied onto a string, and at point O could be a person holding the end of the string, twirling the ball around their head. There could be any number of reasons why a particle moves in a circle, but there must be an unbalanced force pointing towards the centre of that circle that causes the centripetal acceleration. That's a fair bit to digest in this video. The little animations here are nice to help us visualise, but that's the real deal there. The vector equation for acceleration, we take a time derivative, we notice by moving negative omega squared as a common factor, we're literally looking at a multiple, a scalar multiple of our position vector. That's enough for this instalment. Part 3 coming up soon.